This is a video lecture about section 11.2, and let's look at the objectives that we'll be covering in this section. And the first part is to apply the fact that the probability of an event is a real number between 0 and 1, inclusive of both. That means it could be 0 or 1 also, and any number in between, any real number in between. And know the meanings of the terms impossible event and certain event. Then we're going to identify the correspondences among set theory, logic, and arithmetic. Then we'll determine the probability of not E given the probability of E. And last, determine the probability of A or B given the probabilities of A, B, and A and B. We begin with the fact that we know the probability of an event E is equal to the number of favorable events for E divided by the total number of events. Total number of outcomes. And we also know that the number of favorable events must be between 0, including 0, and the total number of outcomes, which is n of s. When we divide this inequality by n of e, then we get 0 divided by the number of favorable events, less than or equal to, by the total number of outcomes, n of s, less than or equal to number of favorable outcomes divided by the number of total outcomes, less than or equal to n of s divided by n of s. Now 0 divided by the total number of outcomes, of course, is 0, less than or equal. And again, this expression here is equal to the probability of E. So we say then that 0 is less than or equal to the probability of E. And any quantity divided by itself, less than 0, is equal to 1. So this then tells us the probability of a favorable event E is between 0 and 1, including 0 and 1, because we have less than or equal expression here. So here's the official designation of properties of probability. Let E be an event within the sample space S, that is, E is a subset of S. Then the following properties hold. Number 1, the probability of E is less than or equal to 1 and greater than or equal to 0. So in other words, it's a number from 0 to 1 inclusive. That means we include the endpoints 0 and 1. Number 2, the probability of an impossible event is equal to 0. And number 3, the probability of a certain event is equal to 1. Let us apply this knowledge to some example. Let's say a single fair die is rolled. Find the probability of each event. The first event is the number 2 is rolled. So the probability, since there's only 1, 2 on a die, would be the probability of a 2 would be only 1 out of 6 sides. That's the probability that 2 is rolled. The second one says a number other than 5 is rolled. Well, what numbers are there other than 5? Well, there's 1, there's 2, there's 3, 4, and 6. So there are 1, 2, 3, 4, 5. So the probability of other than a 5 would be 5 out of 6, or 5 divided by 6. The third one is, what's the probability the number 7 was rolled? Well, on the 6-sided die, the number 7 will not come up, so we are dealing with an impossible event. So the probability of a 7 is an impossible event, so that's equal to 0. The next question is, a number less than 7 is rolled. What's that probability? Well, since all 6 of the possible outcomes are less than 7, the probability of a number less than 7, a number less than 7 is 6 divided by 6, or equal to 1. In other words, we can be certain that one of the numbers will show up, one that's less than 7. The following table shows the correspondences between set theory, logic, and arithmetic. So here we have the operation or connective and the corresponding symbol for set theory, like the complement, it's like an apostrophe, and the logic is a wavy sign, and in arithmetic it's a minus sign. The operational connective symbol for a union is the letter U you've seen before, and in logic it's like an OR with a V, and in arithmetic it's addition, it's a plus sign. And for the intersection, you have seen that upside down U, and in logic it's the upward arrow, and in arithmetic we use the symbol of multiplication. We just have to be careful that in many cases multiplication is implied. If we write something like 3x, it means 3 times x, and we typically leave out the multiplication symbol. So that can be implied, so you got to be careful with that. And so we're going to use this definition here, to come up with a very important concept. It is something you may have seen before in set theory, where the outside is the universal set, and then some in the middle is a set E. And so then what's outside E is a complement of E, and that's, we use the apostrophe or prime. Now again, that is not universal. Other books may use a different notation, like a bar can indicate the complement of a set. But here they use the apostrophe. And so the logical connective not corresponds to a complement in set theory. The probability of not E means the probability of the universal set S, the sample space, minus the probability of E. So it means 1 minus the probability of E. So that's a very important concept to remember, and we'll be using that a lot. So here's the official version of it in the green box here. The probability of a complement for the event not E. The probability that an event E will not occur is equal to 1 minus the probability that it will occur. So that's a very, very important formula, and it can be used in many cases where the left side is more difficult to evaluate than the right side. And again, this formula will be used a lot more in the future, also in a slightly different way. Let's look at an example where we can apply this principle. And a standard deck of cards has 52 cards, and with 4 suits, and so there are 4 kings. And so by realizing that, we can write this: the probability of not a king, drawing a card that's not a king, would be 1 minus the probability of a king. And since there are 4 kings, we know that that's equal to 1 minus 4 out of 52 cards. And so that's equal to 52 divided by 52. That's our 1. Minus 4 divided by 52. And 52 minus 4 is 48 divided by 52. And that's equal to 12 divided by 13. Very simple example, but it explains the point. So the probability of not drawing a king is equal to 1 minus the probability of drawing a king. So it's 1 minus 4 divided by 52. And then we do the arithmetic on that, the combining of fractions, and that turns out to then 12 divided by 13. Let's look at an example that involves the OR connector. So let's say we have a set of numbers from 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 10. And the first question is, find the probability that the number is odd or a multiple of 4. So let set A designate the numbers, the elements 1, 3, 5, 7, and 9, the odd ones, and set B has elements that are multiples of 4. Then if a number can be an A or the other A or B, or the A union B, that set would be 1, 3, 4, 5, 7, 8, and 9. So that set has 1, 2, 3, 4, 5, 6, 7 elements. So the probability that a number is selected from S that's either an A or B, since we have 7 elements here, would be 7 divided by 10 elements in the sample space, 7 divided by 10. The second question is, find the probability if the number is odd or a multiple of 3. So let's identify set C as the multiples of 3. That, of course, would be 3, 6, and 9. So then A union C, either or, A union C would be the set 1, 3, 5, 6, 7, and 9. So that set has 6 elements. So the probability of A or C would be equal to 6 divided by 10, or that, of course, is equal to 3 divided by 5. This brings us to the topic of mutually exclusive events, and that's very easy to demonstrate in terms of sets. It's here our sample space, and here's set A, and here's set B. So we say that A and B are mutually exclusive events if they have no occurrences in common. In other words, mutually exclusive events cannot occur simultaneously. That's a very simple explanation using sets in this manner. This now brings us to a very important addition rule of probabilities for events A or B. For the event A or B, if A and B are any two events, then the following holds. The probability of A or B is equal to the probability of A and the probability of B minus the probability of A and B, in other words, elements they have in common. And if A and B are mutually exclusive, then the following holds. The probability of A or B is equal to the probability of A plus the probability of B, because then this would be 0, since they're non-overlapping events. Let's do a couple of examples, and the first example is from the experiment drawing a single card from a standard deck of 52 cards. What is the probability of an event, and what is the odds in favor of such an event? So the first question is, what is the probability of drawing a king or a queen? Well, there are 4 kings in a deck of 52 cards, and there are 4 queens. So the probability of drawing a king or a queen would be 4 divided by 52 plus 4 divided by 52, that would be equal to 8 divided by 52, or that would be equal to 2 divided by 13. To find the odds for this event, remember the probability of an event E, if that's A divided by B, then the odds of for this event the odds are A divided by B minus A. So what does it say for this example here? So our probability of a king or a queen is equal to 2 divided by 13. That's the same as 2 divided by 13 divided by 1. So our A corresponds to 2 divided by 13, and our B corresponds to 1. So then the odds for such an event is equal to 2 divided by 13 divided by 1 minus 2 divided by 13. Okay? So combining expressions in the denominator would be 13 over 13 minus 2 divided by 13. So that then turns out to be 2 divided by 13 divided by 11 divided by 13. So there would be 2 divided by 11, or typically we write the odds as 2 to 11. So that is the odds for this event to occur, selecting a king or a queen from a standard deck of 52 cards. Another question would be, what is the probability of drawing from a standard deck of 52 cards that's neither a heart nor a 7? Well, we can write that as 1 minus the probability of a heart or a 7. So let's look at that probability here. What is the probability of selecting a heart? Well, there are 13 heart cards out of 52. And there are 4 cards that are 7s, 4 out of 52. But remember now we need to subtract the overlap between the hearts and the 7s. And there's 1 card, the 7 of hearts, so we need to subtract that. So we have 1 minus this expression, and so that would be 1 minus 16 divided by 52. 16 divided by 52, and so that is equal to 36 divided by 52, or equal to 9/13. So that is the probability of selecting neither a heart nor a 7. And again, by using the property of 1 minus the probability of a heart or a 7. In other words, the complement of neither a heart nor a 7. How do we find the odds? Well, as in the previous example, if an event E has a probability of A divided by B, then the odds for this event, are A divided by B minus A. So in this particular example, we have our A, of course, the probability of the event we are looking for is 9 divided by 13, divided by B, which would be 1. So that then the odds from this would be 9 divided by 13 divided by 1 minus 9 divided by 13. So that would be equal to 9 divided by 13 divided by 13 divided by 13 minus 9 divided by 13. So it's 9 divided by 13 divided by 4 divided by 13. And let me just explain one time how we divide a fraction by a fraction. You may remember that. We divide a fraction by multiplying it by the reciprocal of the second fraction, so times 13 divided by 4. So then that is equal to 9 divided by 4. So the odds for this event are 9 to 4. As a last example, let's consider a student who's doing a certain number of hours of homework, X, 0 hours, 1, 2, 3, 4, 5, 6 hours. And here are the associated probabilities of doing that many hours of homework. So there's some questions, some probabilities we like to consider. And number 1, what is the probability of studying fewer than 3 hours? Fewer than 3 hours. Well, we just look at that, and fewer than 3 hours means 1 or 2. So that's a probability of studying 1 hour plus a probability of studying 2 hours. So that's equal to 0.05 plus 0.10, or equal to 0.15. How about the probability, computed probability of more than 2 hours? More than 2 hours. Well, there are two ways of doing it, really. And one of them would be to simply add up the probabilities of studying 3 hours plus the probability of studying 4 hours plus the probability of 5 hours and the probability of 6 hours. And that would be equal to 0.20 plus 0.40 plus 0.10 plus 0.15. And that turns out to be 0.85. course, the other way we could have done that is to compute the probability of studying more than 2 hours is equal to 1 minus the probability of studying less than 2 hours or less. And so that would be equal to 1 minus, well, the probability of 2 hours plus the probability of 1 hour. So it would be 1 minus 0.10 minus 0.05, and that of course is also equal to 0.85. 0.85. So we could use a complement in this case also to come up with the same answer. And let's say, what about the probability of more than 1 hour, but no more than 5 hours? So, probability of more than 1 hour so that would be equal to the probability of 2 or 3 or 4 or 5 hours. And so those probabilities, when we look at the table, is equal to 0.10 plus 0.20 plus 0.40 plus 0.10, and it would be equal to 0.80. So that's a probability of studying more than 1 hour, but no more than 5 hours. And the last question would be, what is the probability of that student studying fewer than 5 hours? So the probability of fewer than 5 hours So here we use a complement, and we find out that it's 1 minus the probability of 5 or more hours. 5 or more hours. So that's equal to 1 minus the probability of studying 5 hours or 6 hours so it'd be 1 minus 0.10 plus 0.15, so it'd be equal to 0.75, pardon, 0.75. So this is how you can use the OR part of the calculating probabilities combined with the complement, using the complement approach. This concludes section 11.2, and I would just recommend that you do all the examples in section 11.2 in preparation for your online homework assignments in MyLab and Mastering.